Hi, everyone. Welcome to the talk today on fast, high-quality pseudo-random numbers for non-cryptographers. I'm not only can I not say it, I am not one. I'm Roth Michaels. Thanks for coming today. We're halfway through CppCon. Hope everyone's having a great time. Before we get into the talk today, just a little bit of a disclaimer. I know some people are very passionate about const east, const west, tabs versus spaces. And if you want to talk to me about it later, I've become accustomed to a both style that we use at work. Don't worry, it's formatted by tools. And also, Emacs versus Vim. There's similar, very strong opinions about random number generators that are not in the standard library. And you can go on Reddit and read those flame wars. I'm not here to answer that. I'm here to tell you about my own exploration to answer some questions in this territory, what I found and what I still don't know. But I'm certainly not trying to crown the non-standard library PRNG king or queen. So a little bit about myself. I'm Roth Michaels. I'm a principal software engineer at Soundwide, which is a parent company of Isotope Native Instruments and Plugin Alliance, Brainworks, and SoundStax. We make software for audio production, so that's both instruments and production, live performance, mixing and mastering of records, and post-production cleanup for television, film, and radio, and things like that. Primarily, most of the software that we make at both Isotope and Native Instruments, while we do have some desktop applications, most of the software we use are plugins that run in some other audio editor or video editing software. So like you see here, there's a few Native Instruments plugins in this session of Logic, which is Apple's audio editor. And the key point to call out here is that is significant for some of the things we're going to talk about is often you won't just have one of our plugins running in someone's session, but you could have 2 or 3 of them, 10 of them, perhaps even 100. And so that means certain things like they have to all maintain individual states. We have no global state. And there's a lot of complications with the fact that we don't control the threading. The host calls into us with whatever threading model they're working with, which has to do with some of the choices that we'll talk about later when we get into talking about seeding random number generators. Just a little bit of digital audio basics, because this will matter for kind of the context of what we're talking about if you're not familiar with it. So digital audio, or really any digital signal processing, the idea is you're taking some analog signal with the red line in this graph and sampling it at some duration, frequency, number of times per second, and some amplitude resolution. So in this particular case, with going from +7 to -8, this is a 4-bit resolution, so you can see it every so often. There's this blue dot, and that's the digital value that represents this analog waveform. So there's kind of a couple pieces of important information here. One unit is the sampling rate, so that's the number of times we measure per second, and that gives you frequency resolution. So essentially, whatever your sampling rate is, the Nyquist theorem says that you can represent frequencies up to half that resolution. So like a CD is 44,100 hertz, which gives you a little bit above what's known as the range of human hearing. In all my examples, and benchmarks, I'm using a sampling rate of 48,000 hertz, which is sometimes used for streaming and DVDs, and is kind of a little bit more high quality, modern standard, and there's reasons I kind of like it for examples. And then there's the amplitude resolution. So 24 bits will give you 144 decibels of amplitude resolution, which is greater range than the human ear can perceive. We can perceive about 120, so that's all the resolution we need, and we can represent that either with 24 or 32-bit float integers storing that information, or often internally we use 32-bit floats because that gives us 24 bits of precision, and then we don't need to worry about overflows, and we can kind of calculate in various ranges. And so a lot of the algorithms we're going to look at, and for my use cases, I'm interested in generating random 32-bit floats most of the time. And then when we're actually kind of processing audio, usually whatever we're running in, we'll have some callback that will call some process function on us that will take, usually not APIs like this, but for CppCon, we're using span. So in this case, this process call will take a span of floats that's our buffer that the host gives us and is asking us, hey, please fill up this buffer with audio samples, and we have to do it in time or else bad stuff comes out of the speakers. And usually it's not just a span, it would actually be something multi-dimensional, because you would have maybe a buffer of 512 samples that the host asks you to process at a time, so you're not processing whole seconds, but just little few milliseconds at a time. And usually you actually have a span of spans because you have multiple channels of audio, like your left and right, if you have stereo or more channels for surround. So a lot of the questions that came up today, I started thinking about a few years ago when we were working on this product Neoverb, which is a reverb product. If you don't know what reverb means, we'll have some sound examples later and you'll get up to speed. But this product has 3 places where it needs to use random number generators. And I wanted to do a good job, and there's actually important reasons the random numbers are here to make sure when you have multiple copies that they don't kind of create buildups in certain frequencies. Just the way the reverb algorithms work, that can happen, so the random numbers kind of help you deal with that. But some questions came up in my mind. First of all, I was using the standard library random number generators, and we'll talk about them in a minute if you haven't heard of this, but the kind of popular random number generator is called MT19937. And I wondered, okay, well, if I have a whole bunch of these instances and I want to do a good job seeding them, what's the best way to do that? And I started reading about this stuff, and I found a bunch of blog posts that talked about some challenges we'll get into, and those same authors also were talking about their own random number generators that they say are better than what comes in the standard. And supposedly there's a couple statistical tests that this random number generator fails, and also some people say it's slow. We'll get into that in a minute. So I started to wonder, should I look for generators outside the standard? And then also there's this concept of distributions. Again, if you don't know what that means, we'll get into it. But basically when you take a random number generator, how do you get that into the range of values you care about? And I was getting kind of conflicting reports about this. There was a talk from Timur last year, which I'll link to in a moment, that was talking about real-time safety in the standard library. And he brought up the language of the standard library, hints that maybe you can't trust these standard library distributions. And I was wondering, is that really true? Do I care about those concerns? And then Walter Brown also had a great talk on random number generators where he says, even if you don't think you care about it, just please do it right, use the distributions, because who knows, your code might end up on Mars someday. And then so I was thinking about this stuff and wondering about other algorithms, and I presented this at a post-CppCon talk, and one of my colleagues mentioned, oh yeah, I'm already using this algorithm Zoshiro 128 plus out of the standard library. Yeah, it's great, you should use it too, it's fast. And why me and others didn't start using it is he wrote the algorithm in a kind of a hand-coded class and didn't conform to the concept of the standard library, so it wasn't something we could easily plug and play and swap out. And you'll see a little bit more kind of what I mean by that also in a minute. So for reference, there's this great talk from Walter Brown about the random number facilities in the standard library. I recommend you check it out to learn more about this in general. And here's the reference to this talk from Timur last year, which has lots of great analysis about real-time safety in the standard library and kind of maybe even wonder more about these questions I was wondering about. And like I said, my colleague was already looking into this. I'm not exactly sure how we did this benchmark, but this is something that he's been doing since before I arrived. He has this way of measuring stuff and painting out some lines. You probably can't read it, but the top line up there is the Zoshiro Plus that he likes. The green line below it is the MT19937 from the standard library, and you probably can't make it out, but it isn't much of a solid line because that generator actually has non-deterministic performance. It gives you really fast numbers, and then every now and then has to pause and do some work. And we'll get into some of the other things that are on this chart, but I just want to show that to just show that, I'm not the only one asking these questions, and everyone kind of takes different approaches to looking at how to answer it. So I was really wondering, what do I really care about? In digital audio, obviously I care about performance, but are these things really going to impact me on the big picture of my product? And what do I care about quality? As I said, there's these big debates online about one random number generator versus another, statistical tests, do they correlate if the seeds are next to each other? And frankly, I don't care about the statistical value of the bits that come out of the random number generator. I care about if the audio result after I get those bits, do a whole bunch of other work, and I have audio coming out your speakers, does that give the result I want? And if I have multiple instances, do they sound different in a way that humans think they're different things? And then does any of this really matter, or can I do anything and get a fine result is something I kind of am hypothesizing. And this is a part 1 of 2 talks. I'm giving kind of a part 2 at the Audio Developers Conference in November. And for that, I'm going to look into a little bit more the results of the audio that we get out and actually, is it good enough both from a numerical analysis perspective and also actually blind listening tests. And I'm going to make some various people I know listen to a bunch of things coming out the same processor and see if they can tell the difference, which one sounds better. And my theory is that maybe they won't, and we'll see a little example of why. Can I see a show of hands? This is a set of coin tosses. I'll show you a few of them. And I'm curious if this looks to you, if you believe this is a random sequence of heads and tails or a non-random sequence of heads and tails. So if you believe this looks random, raise your hands. Maybe about half the room. What about this one? Maybe a little more. What about this one? Okay, about the same, about half. What about this one? And we got one more. And so I'll tell you the trick here. We'll go back to the beginning. This is not random. I pick these heads and tails myself. This is a 100% creative deterministic algorithm. This is from the standard library random number generator. So this is a pseudo-random sequence of numbers. It's good that half the room believed it was random. This one was actually a coin toss I did this morning. And I did more than 10, and I kept getting tails. I don't know which state quarter this was, but I could not get it to flip heads. Again, standard library. And kind of my point here is, with human perception, deciding what counts as random is very different than a statistical analysis, and we care about very different things. And because, I won't get into the neuroscience of it, but a lot of what we perceive in the world is our brain missing a lot of information and filling in the blanks. So when we're thinking about things that we see and hear, what quality means is maybe different than what statisticians think about. So when I talk about random, what is a random number? And there's kind of maybe three categories to think about. There's truly random numbers. There's pseudo-random numbers, which is the kind of main point of this talk. And then also quasi-random numbers, which I don't know a lot about, but I'll mention, and also why that's not particularly interesting to me. So at the moment, I might explore it at some point. So random numbers are things that are like truly random and non-predictable things. So that is like theoretically maybe a coin toss or a fair die roll. Theoretically, computers come with random devices maybe, like /dev_random and /urandom that supposedly can build up enough entropy to provide random numbers. You can read various things online about why maybe that's not true. I know back in the day when you'd make RSA keys, they'd ask you to move your mouse around to add entropy. I don't think they do that anymore. But maybe they're random, maybe they're not. I'm not the one to make the judge on that. But there are some really cool ways to actually get real random numbers. There are devices to measure atmospheric noise to give you random numbers, radioactive decay of something that whenever some little bit of radiation goes off, that can trigger a bit or not bit. And a really cool one, you can use lava lamps for random numbers. So this is something that Silicon Graphics actually had as a service, the Lava Rand, where they had a lava lamp and a digital camera looking at it. And when you requested random numbers, it was somehow, I don't know what they did with all the pixels, but that was their source of entropy, was a digital camera looking at a lava lamp. And I dream of having one of those to see my random number generators one day. I just think that's super cool. And then to mention quasi-random numbers recently, and also sometimes called low discrepancy sequences. And these are things that are designed to eventually fill out a uniform distribution, but they have a much more predictable pattern to them than a pseudo-random number generator. So if you look at the squares in the bottom three on the bottom row, you can see there's actually kind of seems like kind of a predictable pattern you can notice of the dots on the screen. And that's why I'm not particularly interested in looking at those. I forgot to mention this in my intro, but my background and actually how I got into software development was as a composer and making software for my experimental music. And something I've discovered is humans are really good at noticing when things are exactly the same. If they're a little bit different, you don't, but exactly the same, we notice repetition really easily. So my hunch is that these are not great noise sources for music. And so that's why they're not part of this talk today. I might look into it at some point, but we'll see. But a pseudo-random number, that's what we're here to talk about today. And that's a deterministic algorithm that approximates randomness. So theoretically, you shouldn't be able to easily predict the results, and they should statistically and perceptually seem random. And I guess I decided to write that slide twice and didn't delete one of them. So we have a few use cases for random numbers, cryptography, slot machines, and those are not the category of this talk because those actually need certain properties of like actually not being able to reverse them. And I'm not a cryptographer. That's not the kind of generators we're looking at. Monte Carlo and other simulations need random numbers. Machine learning, so both initial weights. Yeah, oh man, yeah, oops. I knew that looked wrong when I typed it and I couldn't figure out which letter was wrong, thank you. I even looked up that I could spell it right and I spelled it right when I looked it up, but yeah, that should say Monte Carlo. But so in machine learning algorithms, both the initial weights for training neural networks are come up with random numbers, as well as generative networks that like make up images. Like there's a lot of cool things that we've seen coming out like that. Usually using some sort of random noise as input. Video games might need random numbers. Pinball, I have those separate because my theory is pinball with all the human physics involved probably needs lower quality random numbers because you have so much other physical entropy happening. VFX, graphics, and audio is what we're here to talk about today. And for all of these, you might have different concerns about quality, whether you care about portability and results across platforms. Like your simulations, you might want to be able to run it on a Mac or Linux, or maybe not. Maybe it only matters that your results are the same on your particular supercomputer. So we'll talk about portability a little bit after the quality talk. So let's start off with a really bad example about random numbers, how to roll a six-sided die. So we have this function d6 that we'll call Pseudo-Random, which is also the crand function, modulo 6, and then add 1 to give us a random number 1 through 6. STL has a great talk about why you should not use Pseudo-Random and goes into lots of detail about all the problems that it has, and just kind of summarized in this slide. But there's really one reason why I just don't care about Pseudo-Random. It's not thread safe. And like I said, we're dealing with multiple copies of these plugins in one session, and they can't all share one unthread safe random number generator. And so we don't use this in our code, although I did find one when I first started because we switched our regression tests from running serially to in parallel. And all of a sudden, one non-deterministically failed because it turned out there was one Pseudo-Random in our code base. The other issue is the modulo 6, because this is not going to give us an even uniform distribution and a truly fair dice roll. And the reason for it is, if we think about it, does anyone have an idea of if we have a six-sided die and I want to generate numbers 1 through 5, how do I do that?
Rejection something.
I'm sorry?
Rejection something.
Yeah, so we could.
Just roll the 6.
Yeah, re-roll the 6s. And that's actually what the, when you ask for a uniform distribution, that's actually how they work in the standard library. But there's a tougher question. What if I want 1 through 7 out of six-sided die? I'm not really sure. Don't worry about it. We'll see how the standard library will just take care of that for you. Let's not invent that ourselves. So here's the better implementation with the standard library, and we'll go over the few pieces here. First is this Pseudo-Random device. And so that's how we're getting our initial seed. And this is how we actually access the computer's idea of its true random source. It might have problems. It might not actually be a true random source. It could be a pseudo-random number generator. It can run out of entropy. It can block. It can give you 0. But this is the basic example. You get a random number from the random device as your seed. And then we use that to instantiate a random number generator. In this case, MT1937, also known as the Mersenne Twister, which is considered the high-quality generator in the standard library. We create a distribution. And so this is saying we want uint8s from 1 to 6 to come out of a random number generator. And to get a random number, we call that distribution D by passing it a generator, and it will use that generator to call it as many times, like re-roll that 6 or re-roll that int max, because the int max is going to not be a fair dice roll. And very quickly, because this will relate to some of the other examples we look at, if we see a fair dice roll as a class, it might look something like this. And I just want to point out, see this distribution is a member, but look, it probably doesn't need to be because initialized like that. You know, maybe we could put it static here in this roll. Maybe it doesn't need to be static because these are actually often quite cheap to create. We can just make it like this. And this has various performance trade-offs you might need to measure for your situation. Check out this talk for some more examples and surprises about that. But the reason I'm putting it here as a member is because in general, distributions and generators go together, and not all the distributions can safely be created and destroyed. Like, for example, a normal distribution actually makes 2 numbers at a time when you call it. And so you call it once, it generates 2 numbers, gives you the first one. The second one is, oh yeah, I've got this number ready, I give it to you. So some of them have state. And so don't just blindly create them on the stack unless you're sure that distribution doesn't have any state. And the other reason I'm setting them up like this is because some of the benchmarks we go into, we care about state. So just every example I'm using, I'm going to set it up this way as a member just for consistency. Another few things we might want to do is keep track of what seed we created this with. So if we make this and roll some dice and then want to like recreate this again for some unit tests or reproducibility, we might want to print out the seed we started with and then have some alternate constructor where we can actually set the seed on construction. And that's something we're going to get into a little bit later to think about, like, how do we remember seeds, reuse them, and think about generating seeds. So, this comes to the question, oh, I am full of typos. I know how to see MT1937, but I didn't know how to seed it well. And so I was reading about that, and I found these 2 websites, one about the Zoshiro family of generators by Sebastiano Vigna and David Blackman, as well as the PCG generators by Melissa O'Neill. And both of them do a lot of writing about random number generators, trade-offs, and other things. So I kind of, that's where my learning and questions about this really started. And on Melissa O'Neill's blog, when she talks about problems with the standard library, Mersenne Twister, she brings up this thing called the Twitter problem. So similar to our example before, we create a Mersenne Twister. In this example, we want to say, well, if we get the result 7, that's going to be the one special time we do some extra logging. Well, it turns out, if you do this, you're never going to ever get a log message. Same thing if you pick 13. The reason for that is that the Mersenne Twister has a really huge state, and you can't initialize it to every possible state with just a single integer. So if you seed it with 1 integer, you will, there'll be numbers like 7 and 13 that will never be the first number you get. So just something to keep in mind for examples like this and why seeding is complicated. And this slide is out of order, so I'm going to skip to this one. The slightly better way you could seed it, perhaps, is using a seed sequence where you provide multiple seeds, and then the seed sequence object can actually generate as many state values as necessary to fill up the object. There are some downsides. Apparently, seed sequence can get stuck in what's called zero land and give out a bunch of zero-oriented numbers. I don't really know all the downsides. You can check out Melissa O'Neill's blog about this. But not only is it has supposedly some downsides, this also seems a little inconvenient to me. So what I took away with this is there's some pros and cons to the Mersenne Twister. One, it seems really cool. It has this really large period, 2 to the 19937 minus 1. Well, if I think about if I'm going to like make a random floating point value every 48,000 times a second, every second for a 3-minute pop song, all right, so that's 48,000 times 60 times 3. That's way smaller than that period. I don't need way that many random numbers before I'm gonna be done playing music before that ever is gonna repeat. Supposedly it's high quality, but it fails some tests. I kind of like it because, yeah, Mersenne primes sound kind of cool. I mean, not as cool as Fibonacci numbers, the golden ratio, but that sounded neat to me. And also, personally, Mersenne was also one of the first people to write a book on music theory and kind of really established the rules of how string vibrations work that Pythagoras came up with. So I thought that, it seems cool, but it's hard to seed. It's maybe slow, and it fails some statistical tests, so maybe I want to find something else. But so speaking of seeding, let's talk about kind of a few strategies you could use for seeding. Like we saw in the examples, you could use a random device, perhaps combine it with seed sequence. Sometimes people use time, but time is not really a great seed because depending on your resolution and how quickly you seed 2 things, you could end up with 2 generators with the same seed by accident. Also, there's nothing really particular to think that like, oh, the right now time is somehow a better seed than 42 or something. Although some generators don't do great with seeds with a bunch of zeros. But really for me, and a lot of simulations, I think the best way to seed it is just start with some seed, whether randomly generated or picked, and just seed all of your various simulations or devices and plugins with just a sequential number. Because you have hopefully your generator is good enough that that works, because like, why would I believe that randomly picking numbers is somehow going to magically give me a better result than just seeding with sequential seeds? Also, a lot of generators allow you to quickly discard a whole lot of values. So you can actually start with one generator and like copy it and then say, okay, jump ahead a million values, and you use the same seed, but they're out of sync. So thinking about why I care about sequential seeding, like I said, we could have multiple of these plugins running in a single host application. So let's say I created 3 of these, and the first one got seed 42, 43, and 44. Then I'm done working my project, I close it down. I don't want to open it up and get different seeds for the different copies. So I want to make sure that however I'm managing my state, I'm saving that seed information so that I get the correct seeds back when I reload the session. So I start from blank, I reload up, okay, these guys got the correct seeds, and now I want to make sure that if I add something new, it also, in the second day I'm working, that it also doesn't have a seed. Don't know what that slide's doing here. So here's my solution for this, something I call the seed pod. Hopefully this is, I have some zoomed in slides in case it's not big enough to read. So essentially it starts with some particular seed, and it's an atomic counter essentially for handing out seeds. So the new seed method essentially does a fetch add and returns the result to give you a new seed. It checks if it's 0, because not all generators can handle being seeded with 0, and just skips ahead to 1 if it is. And so here's how, as we add new instances in our first session, we're getting new seeds. And then when we reload our session, we have this claim seed function. So if someone comes up that already existed and said, hey, I'm already seed 42, they will claim 42. And like, let's say the next seed was 40 in our atomic counter. Well, we'll skip ahead to 43 because we know, okay, 40 already happened, so we want all new seeds to be after this. So if there's something you might want to look into if you want a thread-safe way to sequentially seed a bunch of stuff. So as I said, I was looking into kind of what was outside the standard library and wondering about, well, what's up with these other generators that are supposedly better? So I have links here both to the Zoshiro family from Vigna and Blackman that I mentioned, and then the GitHub to a C++ implementation that I found. Doesn't quite conform to the standard library. Stay tuned for a PR for me on that. The PCG family from Melissa O'Neill and her website and an implementation I'm using for these tests. And then there's also the random 123 collection of generators, and particularly I ran some tests with Philox, which is being proposed for the standard in paper P2075. And that's kind of a different kind of generator from the rest of the family, because instead of just taking a seed, it takes a seed and what they call like a counter, which essentially, I'm not an expert in this, but I believe is essentially hashed with the results. So essentially what that lets you do is have one random number generator, and let's say we seed it with 42, and then you can actually have say, okay, generate me a sequence of random numbers, and then you can use that counter to essentially hash that, so you have a whole bunch of different threads that have different sequences, all generated from like a single seed. Apparently it's kind of reversible, and as we'll see, for my use case, it's maybe not fast enough, so that's why I didn't look into understanding those too much. So in the Zoshiro family, we have a few different generators. There's these star and plus versions, which are different ways that the results are scrambled. And the plus versions are specifically designed for doing 32-bit float numbers, because the lower bits are not of high statistical quality. But you don't need those all 32 bits to make a floating point 0 to 1 number. You only need the top 24. So that's why those are looking for that. And then the bottom 3 are, the yellow ones there all generate a 32-bit result, which is what I care about for my use cases. So that's the only ones I'm going to kind of look at in any tests. The top one is the 64-bit one, and then also the bottom also generates 64-bit, but with a smaller object size. And there's also some even bigger and smaller generators for specific use cases. So a couple of things that I like about the Zoshiro is the way it seeds. It just is recommended to take a single integer seed, run it through a split mix 64 random number generator, and use that to fill up the 4 or 8 or however many integers of state you need. And for my goal of coming up with a bunch of single sequential seeds, that's nice. I don't need to come up with some big sequence to seed with. The PCG generators, there's two basic generators, the 32-bit result and the 64-bit result. These are templates for, or usings for templates that allow you to kind of customize parameters, but not a PRG expert, I don't get into customizing the algorithms. And for seeding this, O'Neill provides her own new seed sequence that fixes some of the problems she points out with the current seed sequence and recommends you use that for seeding. You can also seed with a single integer, and it does a little bit of scrambling to do that. And then these generators propose the standard. We have two 32-bit generators and two 64-bit generators. And those you both seed with a single integer seed and a single integer counter. So we're going to take a brief detour for a demo time to show you some audio examples of the real use cases we're going to, I'm talking about for analyzing like what I care about in random number generators. So the first one, I'll only blast you this for a minute, is generating white noise, which is something used in synthesis and actually all over the place in digital audio is either a uniform distribution of samples or a Gaussian distribution, and sounds something like this. So that's the basic example of like, yeah, I need a bunch of 32-bit values from -1 to 1 to make my white noise. The other example we're going to look at is this plugin called Vinyl, which is a simulation of like making your sound go through a vinyl record. So if we turn on this synthesizer, I don't know if you can hear the dust happening. Maybe I'll stop. Maybe it's coming through very quietly. You can hear some dust coming through there, which is, and we'll talk a bit about actually how we do that, and then we can make scratches on the record. And so obviously the idea here is we want multiple copies of these. We want all the scratches to be in different places. And the third example is a reverb, and this is what we were talking about when I kind of came up with these questions. And so, for example, so that the reverb is that echo sound. And the random numbers we're looking at have to do with this control, which, as I said, is just, won't get into the details, but it's something to make sure that as this tail builds out and you have multiple copies, that they don't interfere with each other. I'll stop this briefly to also just mention, I'll turn down the sound because we don't need to listen to this for a second. But looking back at the white noise example, something that I have some data sets, but my analysis scripts, I think, had some bugs, so I didn't want to present conclusions from this. But something I was interested in looking at was looking at the correlation between multiple audio results and comparing that with performance, and if together, under one p-value, do we see like a significant result? And so just to kind of show you what I mean by correlation, if that's not familiar, these are two different white noise signals coming in, and you see this reddish white line in the middle. It essentially means they're neither completely decorrelated nor completely correlated. And just to show you the difference, if I unplug the right side and so that both channels are getting the same noise source, you see now the white line jump to the top because they're completely correlated. So that's something that I might investigate in the future for the part 2, although I'm not convinced that's actually the most interesting quality metric. Anyway, back to the slides. Okay, so let's talk about some benchmarks on these different algorithms. So for the benchmarks I did, I'm using this Apple M1 Max Xcode 13.2.1. That is not what we use from production for building isotope software. Sampling rate is 4,800, and for any of the audio benchmarks we did, buffer sizes were either 512 to simulate real time or 8192 for a simulation of kind of an offline process. So looking at all the 32-bit generators I was interested in exploring, we see some from the standard library and a few others that I mentioned. The one I highlighted in yellow is actually a 64-bit generator, and I only put it up here because it was such a winner on performance that I just wanted to mention it, even though I only cared about the 32-bit generators. And so on raw generator output, the Zoshiro 128 Plus is fast as we expected. PCG is also very fast. Interestingly enough, a very simple Zor shift, which is kind of the older algorithm recommended by Teamer in the real-time audio talk, is actually is a bit slower than the newer Zoshiro, which is a variation in that, which is faster and higher quality. And then we see the random 1, 2, 3 are even slower than the Mersenne Twister, so I don't want to get into those. And then actually some of the simpler generators in the standard actually are giving slower results than the Mersenne Twister, so I was interested in exploring their quality, but since they're slower, I'm not going to look at that. So we don't need to look at all this code, but essentially for kind of some of the initial, those benchmarks were generating uniform white noise, which were essentially every sample calling a distribution from -1 to 1 and maybe multiplying it by some gain factors. This is what it looks like for Gaussian noise. And so that's how we made those things. Now, for the vinyl record example I talked about, there's kind of two different things we're doing. We have a dust generator and a scratch generator. So you see this dust generator, it has a random generator that's templated, so I could do some experiments. And it has a real distribution from 0 to 1. That's the kind of when the dust happens. And then an int distribution of the number of dusts. So there's 13 different types of dust we have, and that we randomly pick them. And similarly, a scratch generator is very similar. It has only 3 different scratches we're picking from. And the only difference here really is, I don't know why it was implemented this way, but we generate an int before a float in one and the other way in the other one. And so speaking of those scratch generators, I want to show kind of a naive way to look at some quality. So the goal is to make 10 scratches on a record, and we want to have multiple copies of this thing, and we don't want them to have overlapping scratches. Could somebody, any volunteers want to give me a seed number? 17, all right. And we can start off with the Mersenne Twister. And oh, 2 dashes. And we'll try out sequential seeding. We'll do another one that says seed 18. And if I look at these, what these audio files generated is kind of representation of the timing of the scratches on an album. And I should probably I'm just lowering the gain on these because I was generating values between 1, 2, and 3. So you can see, and I'll get rid of the spectrum analyzer. This is the pattern of scratch choices that were made for one of them. So you see we're only choosing between scratches 1 and 2, and we have that timing. And these are often picking, maybe scratches 3 in there, and it has a different timing. So, hey, these are 2 believably differently scratched records, and we'll see similar results with others. And so I have another test to show, well, how many scratches can we do in a row? So we'll start back with our 17 seed. And so this basically, what this test is doing is I'm running scratches over and over again to the same buffer and basically seeing, do any of my scratches collide in time? So I can create, starting with C17, the Mersenne Twister, I can create 29 different records before a single scratch is in the same position, which I think is probably good enough on quality. And we can see, if we do Zoshiro 128 plus, 26, that's all probably pretty good. And that varies depending what seed you pick, and PCG 32. Oh, wow, that's a great result, but I probably don't need 100 different vinyl simulations in my track. Just to show you one other quality measurement, we can look at a few of our, let's check out our Gaussian white noise examples. So we can pull in a Mersenne Twister with that seed, get PCG with this seed. Oops. And let's go for Zoshiro 128 plus with the same seed. And if we were to analyze the spectrum of this, select all, it's super flat, which is what we expect for white noise. Same thing with PCG, and same thing with Zoshiro. So making random noise samples for the length of a pop song, you're going to get white noise out of all these generators. Now, if you look at maybe a few seconds, it's not quite as flat, but it's pretty flat and ripply. So I'd say all these generators are perfectly capable of making white noise to a believable result. So let's get back to the slides. And so obviously I think there's other things I want to investigate for really are these high quality, and do some tests with many, many, many more results than just a couple seeds. But I think that's kind of a good way if you're just putting something together quickly and you want to like see like, hey, do these suck, or am I getting different results that might be believable? And I think in this case we got believable results. So now that's kind of some of the stuff I want to talk about the different generators and quality. We'll get to one more performance analysis at the end. But another thing to think about is the distributions. And there's kind of two problems with them. One is they're not portable. Every platform can implement the algorithms differently. For example, Clang might hand you out one of the two normal distribution numbers one way. MSVC might do it another way. So if you care about platform portability, you might not want to use the distributions from your vendor, but you might want to use Boost, or you might want to take either Microsoft's or Clang's standard library, which is open source, and say, okay, I'm going to pull in this copy of the distribution and use it for all my platforms. But maybe your simulation only runs on one system, and that's fine. And for us, we don't expect Mac and Windows or M1 and Intel versions of our software to perform bit for bit exactly the same. So I think probably we don't care about that, and we're happy to use things even if they're implemented differently in different standard libraries. The other issue that Timur pointed out in his talk is the distributions have amortized cost over time. Like we saw in the rolling the dice example, they might have to just generate more bits to actually get you a real result that fits in the uniform distribution. Unfortunately, and so that could matter for a uniform int distribution or a uniform real according to the standard. Both of them have amortized cost. But if we look a little deeper, we know the int one might have non-predictable performance, but I think we can trust any real distribution when we're making floating point values, which for audio, uniform real is our most common tool in the toolbox. And the reason we can probably trust that is that the standard library provides this feature, generate canonical, which at least Clang does, and in general is probably the way you would want to implement a uniform float distribution, is by getting a 0 to 1 result out of your random number generator with this generate canonical. And if we look at this math, I'm not going to go over it in detail, but basically it says if your generator outputs at least 32 bits, you're going to be able to get a uniform float 0 to 1 with a single call to the distribution. You're not going to need to call it once. Same thing, if you have a 64-bit generator, you can get a double with a single call. So I think actually we can trust uniform float distribution to only ever give us one result. But as Timur points out in his talk, the uniform int definitely can call your generator more than once. That might have different performance, buffer to buffer. Maybe we don't want this in real time. So I did a test. I'm happy to show the code. I didn't actually put a slide in here for it, but essentially I made a couple what I call simple distributions. The simple uniform distribution is just I use the modulo from the early slides. I don't actually care about it being uniform. I just get it into the range. Simple real distribution, I use some math that is a that actually Vigna on the Josiro blog says is a good way to get a 32-bit value out of a random number generator. And so I did kind of two tests. Use the standard library for both distributions, just use the modulo for the int when I'm generating dust, random dust, and still use the standard library for the timings of the dust. And then also a test where I use the uniform int, just a simple modulo, and my own calculation for making a float instead of the uniform real distribution. And we see with both the Mersenne Twister, Zoshiro 128 Plus, and the PCG, we actually do save time by doing the naive modulo and not getting a truly uniform distribution. My own attempt to do better than the standard library and real, as you can see, actually slows stuff down. So there is some validity what Timur is saying about if you need to actually be sure your buffers get exactly predictable performance, you might want to sacrifice a little bit of quality on your uniform int distribution. Because if we think about our dice roll and the size of a 32-bit int, do we really care if 5 and 6 show up one less time out of all the times than 1 through 4? Maybe nobody will notice. But I'd say this difference is actually probably not enough difference for you to care about, and you should stick to the standard library. And the reason for that is what I see when I do an end-to-end benchmark of NeoVerb, that reverb plugin. I'm not doing a micro benchmark, but I'm taking the entire product, running audio through it, and we have a tool for doing this benchmark, and seeing the result with different generators. And you'll see it's kind of interesting. So first we'll look at Zoshiro 128, my hunch of the kind of simple one that I like the interface I want to use compared with the Mersenne Twister. Are within a confidence value of 95%. We look at 3 benchmarks: startup time of the product, real-time DSP processing, and offline. And when we look end-to-end the whole product, even though we know Mersenne Twister is much slower than Zoshiro 128 Plus, reverb is a complicated algorithm, and random numbers are just a small part of it. And ultimately, it turns out it didn't make a difference. Same thing, here's the CDF for the real-time processing, for the offline processing. And the same thing with PCG versus Zoshiro. That I expected them to be kind of equivalent and similar graphs. So my conclusion here, maybe none of this matters. You can just use the standard library, get fast, good results, and be happy. But if you care about seeding strategies and things like sequential seeding, I do think that the Zoshiro libraries have some nice features. I'm curious to continue exploring whether this 128 Plus, which is only really for floats, is actually good enough to use for ints as well. Because often we'll make one generator, like in that vinyl simulation plugin, and generate ints and floats with the single generator. And I think that probably works. I might want to investigate that a little bit more. And my conclusion is, yeah, stick with the standard library distributions. Or if you care about portability, use Boost or some other open source implementation, unless you can really prove that you really need the performance to sacrifice your uniformity. And thank you very much. And like I said, there's more investigation I've kind of been doing in this, and maybe have some other results that I didn't get into here. So if anyone is curious, just kind of see benchmark code or hear about some of the other results I was not confident enough to put on slides and on YouTube for the end of time, I'm happy to talk about that stuff in the hallway. So thank you very much, and I'm happy to answer any questions. Online question?
We have an online question. What percentage of compute is usually spent on pseudo-random number generators in real applications?
I have not measured that, but I'd say basically, like those sets at the end, I'd say in some cases, almost none. So for example, if we're thinking about generating white noise, I'll turn on my screen mirroring again. So this software I'm using here, RX, actually has like a signal generator, and I can make noise, and I can pick Gaussian or triangle or uniform, whatever. if that's all it does, that's like, this is basically generator number, multiply it by a constant, multiply it by the value in this slider. So it's quite a bit of it. For things like the vinyl record, very small. Like when you adjust the amount of scratches, that is only chosen once when you adjust the scratches. The dust, I don't know exactly how often it happens, but it's probably on the order of a few seconds that we like generate like some dust, and then we play it as it happens, and we run out of dust. We're like, okay, we need some more dust. And so that's maybe a few times a second. And then in the reverb example, it's not every single sample, but it's maybe on the order of every 10 milliseconds, we need maybe 3 new numbers. And there's a lot of very expensive calculations that go on to make a high quality reverb. So I don't know the percent, but it's very small, I think, in these applications. A synthesizer that might have a bit more because like noise is a common thing in synthesis, but a lot of use cases that I'm involved with, it's actually pretty small.
Hi. In example code, it's common to see a generator created to where the numbers are needed. But in a large program, you might need random numbers in a lot of different places. Is it better to create a bespoke generator for each use case or to share a generator across several areas?
That's a good question. I don't know if I have an answer that I'd say is the right answer, but I can tell you what my feeling on that is that, and actually that's part of why I started looking into this, because that reverb was actually a port of a new product, but made using algorithms from another company that we purchased, Exponential Audio. And their random number strategy was that to actually make things kind of have additional chaos in it, is there was a single random number generator for every copy. You might have 10 or 50 of them in your session, and it would hand out random numbers to each one as it asked for them. But because the host application controls threading, the order that every copy asks for those numbers would be different every few milliseconds. So that's adding some chaos. But my thought was, well, since you don't know what's happening, are you actually reshuffling your random number generator into a less random pattern? So it's there's kind of two ways to do it. In that vinyl example, we have one generator that does 2 things, scratch time and scratch choice, and then a different generator that does dust time and dust choice. My intuition is that the more things you use a generator for, if you don't use it consistently, you might actually end up with suboptimal sequences as if you use the generator on its own. But I know it's common for people to use one generator, so I don't, it might be fine, but my gut tells me that I like to have each use case have its own generator and I actually seed them in, I don't know if it's a good idea, but in that reverb, there's 3 different generators. And so when I say it gets one seed like 42, it's actually 3 seeds that are all 42 plus some Mersenne prime plus some other Mersenne prime, and that gives me some naive notion that they won't overlap in ways with other instances. But so for me, I like generators per purpose, but I see others do it, and I don't know that that's a bad practice.
Okay, thank you.
Online question?
Online question. What do you think about parallel random number generation, algorithms involving SIMD and GPUs?
Yes. So in these examples, I'm not using any SIMD, but I believe both the Zoshiro and the PCG generators both can have SIMD implementations. And that's actually quite a common thing we might do in production is use SIMD and actually prepare multiple numbers at a time. I didn't do that in any of these benchmarks, but I think that's definitely useful, especially if you need, in the case for digital audio, if you need a random number every single sample, using a SIMD one is certainly going to be great. And then also, as far as actual parallelism, that's what the random 1, 2, 3 libraries are kind of useful for, where you have one generator, but then every thread has a different hash counter. And that's how they many threads share one generator somehow, I think is the idea, but I'm not an expert in that. Did that completely answer the question?
Do you have a sense of what the jitter is on the different random number generations? You said their amortized cost is constant for Mersenne Twister, but the other ones maybe are less or just less cost overall. Do you know what the variance on the time is for them?
I don't know the variance, but actually looking at what the algorithms are, the Zoshiro and PCG algorithms are completely deterministic time for they do the exact operations every single time you call the generator. They do have some like fancy skips that let you skip like giant amounts with like a single calculation. But unlike the Mersenne Twister, which generates a whole bunch of like new state and then like hands out numbers, the Zoshiro and PCG are very simple algorithms that are scrambling, like they do the whole scramble every time you ask. So you get deterministic performance from those as far as I'm aware.
Cool, thanks.
Any other questions? Thank you very much.